Welcome to our special seminar.
If you want to be on Zoom.
A very special guest, Michael Bornstein. It's a great honor to have you here, Michael. I'm sure we'll learn a lot today. Usually we just have like 30 minutes, maximum 45, but because of your expertise and the relevance of the topics, we felt it's definitely worthwhile to spend a bit more time. We have external guests from the Biostats Institute here in Freiburg as well. And Waldemar, thanks to you for arranging this and making this possible. And we all look, and I personally do as well, look very much forward to your presentation. It might be even a small workshop, I guess, and lots of discussion. So over to you, Waldemar. Thank you. Welcome again.
Thank you.
Thanks, Jörg. Thanks for the introduction. And yeah, we are very pleased to welcome Michael here at the Institute for Evidence in Medicine. We're very happy that you are here today. Before we jump right into the topic, some words for you. We have here a list of signatures where you should sign that this is very important for the medical center, that we know, okay, this is an event, you are here, and yeah. Sign. Okay. What else? We will record this presentation. So yeah, just keep it in mind. I hope it's okay for everyone. And so last but not least, please, for some housekeeping rules, keep your microphones closed, and maybe also the video if there are connection problems. Okay, let me see if I have forgotten something. This seems not to be the case then. Well, Michael, a short introduction for you. Maybe you don't need an introduction at all because everyone knows you, but still I would like to add some little words. So Dr. Bornstein, Michael Bornstein, has over 30 years of experience in meta-analysis, heterogeneity research and meta-analysis. He's the author of the well-known books Introduction to Meta-Analysis. I guess everyone knows this book, and Common Mistakes in Meta-Analysis and How to Avoid Them. Dr. Bornstein is a founding member of the Society for Research Synthesis Methodology and served as its president 2017 to 2018. He's also the primary developer of the software Comprehensive Meta-Analysis, which was funded by a series of grants by the National Institute of Health in the United States. And Dr. Bornstein has published numerous of papers on meta-analysis, particularly in the area of heterogeneity. And that is how much the effect varies across studies and what that means for the potential utility of a treatment. And that will also be the focus of the talk today, Michael. We are very happy. Having said that, I hand over to you and looking forward to your presentation. And after the presentation, we will have some questions and answers. After that, also a get together. Michael, the stage is yours.
Okay. So let me share screen. Okay. Okay, thank you both very much for the introduction. I also especially want to thank Waldemar. We were working together for a long time to arrange this, and I'm very grateful for your input. I wanted to mention, Waldemar had the idea yesterday that I should make the slides available to everybody afterwards. So you're welcome to take pictures if you'd like. You don't need to. You'll get a copy of the slides. And the way to do that is just go to that website on top, meta-analysis.com/papers. And if you enter your email, the server immediately it will send you a copy of the book on common mistakes and the number of papers related to this. And then as soon as we can get the slides up there, it will send that as well. I also should mention, so I don't forget later, that's my personal email address. We'll take questions and answers, well, questions, hopefully answers at the end of the session. But if anybody wants to communicate further and discuss this, please feel more than free to send me an email and I'll try to get right back to you. Before I begin, I wanted to make sure we're all on the same page about meta-analysis, because there's a general conception in many parts of the field that the goal of a meta-analysis is to find the common effect size. In other words, there's an assumption that you're looking at many populations that are very similar to each other, and the goal is to figure out what's the common effect size in studies that are work with that are based on that population. And this is meant to represent that. What we're talking about over here. Everybody, please mute. Okay.
Michael, you can, I'm sorry to interrupt, but you can mute the people by yourself because you're the host. So you can mute all the guests.
How do I do that?
If you click on the guest list, the meeting guest list.
Where do I find that?
It's on the bottom. If you
On the left?
swipe with the bottom, on the bottom of your, maybe Valdemar knows how to do it. Valdemar, could you quickly? Because I can't, I'm not a host, otherwise I could.
Mute all at the bottom.
Okay. Exactly.
Okay.
Exactly. Brilliant.
Okay. Thank you.
That should work now.
Excellent. Oh, we have a lot of people. Okay, good. Thank you very much. Okay, so where was I? Share the screen. So I wanted to make sure we're all on the same page. At one point, going back about 20 years, that was indeed the goal of a meta-analysis. But today, what's more common is that in the meta-analysis, we're going to have studies that work with different populations, maybe different types of interventions, maybe different ways of measuring outcome. And while some, if it turns out that you do that, and you still get a distribution of effects that looks like this, then you can say that regardless of all these differences, the effect size is still going to be very close to that. And an example of that would be all of the studies that were done to look at the impact of a vaccine for COVID. They did them in older people, they did them in younger people, they did them in children, and it always had more or less the same effect. But there are other places where you might get a distribution of effects like this, where in this case, this is the null. And it turns out that for some populations or for some variants of the intervention, the effect is close to zero. For some, it's substantial, and for some, it's very substantial. And in this case, while there's a lot of variation in the effect, they're all positive. It's also possible to get a situation like this, where there are some populations where the treatment might be helpful and others where it might be harmful. So I think we have to be clear that when we're going into a meta-analysis, this is really what we want to know. Is the effect consistent or does it vary? And if it varies, what's the lower end and the higher end of the expected impact? I also want to be clear about one more thing, so to make sure we're all on the same page. We're going to be talking about the prediction interval. When we talk about something like this, we're saying that we would predict that in the next time this is used in a comparable population, the effect is going to fall someplace between here and here. That's very different than the confidence interval. Normally, when you look at the forest plot, there's a diamond presented at the bottom. That's the confidence interval. That deals only with the mean effect. What this is telling you is that on average, the mean effect is going to be something like this. And the confidence interval tells you how precisely we've estimated the mean. So in this case, we can say the mean falls someplace between here and here. But in any individual population, the effect is also going to fall fairly close to that. Here we're saying, again, the mean falls between here and here, but in any individual population, the effect might be as low as this or as high as this. And finally, in this case, we'd say the mean is here, but in any individual population, the effect might be as low as this or as high as this. So the confidence interval is an index of precision. It tells you how precisely we've estimated the mean. The prediction interval is an index of dispersion. It tells you how widely the effects vary. And the only thing they really have in common is the word interval. They're two completely separate things, and it's imperative that you don't confuse them. Okay, now how most papers use the I-square index to quantify heterogeneity, right? Anybody that's familiar with Cochrane, essentially every meta-analysis that's done uses I-squared to quantify heterogeneity. If you look at BMJ or any other journal, more than 80% of them quantify heterogeneity using I-squared. A couple of quick examples. This paper, I think, is from BMJ, the risk of recurrent stillbirth, a meta-analysis, and it says the I-squared statistic was used to summarize the degree of variation across studies, as recommended by the Cochrane Handbook for Systematic Reviews. We considered an I-squared value of 0 to 40% to represent low heterogeneity, 30 to 60% moderate heterogeneity, 50 to 90 substantial heterogeneity, and 75 to 100% considerable heterogeneity. Here's another paper, antidepressant efficacy of this drug. It says heterogeneity in effect sizes was explored by visual inspection and quantified with the I-squared statistic. For comparisons that showed a considerable amount of heterogeneity defined as an I-squared of greater than 50%, we explored possible reasons for the variation. Here's another one. Heterogeneity was assessed using I-squared. I-squared is the proportion of total variation observed between the trials attributable to differences between trials rather than sampling error. An I-squared less than 25% is low heterogeneity, an I-squared more than 75% is high heterogeneity, and so on and so on. So generally what people do is they report I-squared, and then based on that, they'll describe the heterogeneity maybe as being none or low or moderate or substantial or considerable or significant or high. I think it should be obvious that none of these terms is really meaningful because it's going to mean something different to everybody. I mean, imagine if you reported the effect size. We're looking at the impact of the COVID vaccine, and we'd say it's substantial. People want to know whether it's 95% effective or 90% or 80%. Saying that it's substantial is not meaningful. If you report a confidence interval, you're not going to say the confidence interval was narrow. You'll actually give the numbers. And if you report the mean, you're not going to say that it was low. You'll actually give the number. For some reason, when it comes to heterogeneity, people use these terms which are vague and ambiguous. And for me, the bigger problem is that when you have a term like this, it really does not tell you how much the effect size varies. And therefore, what you find in more than 95% of the papers that are published, they mention heterogeneity at the beginning. They might say it was substantial, and they essentially ignore it in the discussion. When it comes to the discussion, they go back to the mean and whether or not it was statistically significant. And I think a part of the reason for that is that they don't really know how the effect varies, and therefore they focus on the mean, which is something they do understand. I did a quick survey of papers that were published in the BMJ. I found that around 60, the way that people reported heterogeneity, around 60% of them reported the Q value, around the same percentage reported the P value, roughly 80% reported I-squared, around 60% reported tau squared, and less than 3% reported the prediction interval. In the 100 papers that I looked at, I found 3 instances where the prediction interval was reported. Obviously, you can report more than one, and that's why these numbers sum to more than 100%. I want to do a quick survey over here. I'm going to show you 2 examples of meta-analyses that were published in top-tier journals. I think they were both in BMJ, and ask you what you think the heterogeneity looks like. The first one is called off-hour presentation and outcomes in patients with acute myocardial infarction. What happened over here, there were a large number of studies where people came to the hospital and they arrived by ambulance after having a heart attack, and they were still alive when they arrived at the hospital. And they looked at the records. They looked at the people that arrived at the hospital during normal business hours. So they had a heart attack, let's say between 8 in the morning and 8 at night. And then they looked at people that arrived at midnight or on holiday weekends or something like that. And the question was, are people that arrive in the middle of the night more likely to die? It's a reasonable question. And the reason it's important to know that the mean effect was very, very close to 1.0. It was 1.1 or something like that, less than that, 1.06, which says that there's a very slight increase in the risk of death if you come in during the night. But the question now is what does this distribution look like? Is it the case that in all the studies, the effect was very close to that? Or is it the case that it varies substantially? Or suppose it varies like this. If it varies like this one at the end, so that in some hospitals, if you come in the middle of the night, you're 50% less likely to die. But in other hospitals, if you come in during the night, you're 2.5 times more likely to die. If this turns out to be the case, it's very, very different than that. If this turns out to be the case, then we need to find out what distinguishes between these hospitals and these. For example, it might turn out that in these hospitals, they have a staff of cardiologists available at night. So if somebody comes in, they get treated. And because it's not very busy, they could treat it immediately. Whereas in these hospitals, there's no such staff. And that would tell us that, if you actually can use resources to have a cardiologist on staff at night, you might reduce the number of deaths, by tens of thousands. On the other hand, again, if it looks, if it looks like, and also, by the way, over here, if it's C, that tells you that the average of 1.06 is really not informative because it's simply the average of two opposites. It would be like if you're asking, does insulin help or hurt? And you have in the study some people that are diabetic and some people that aren't. Some people it will kill and some people it will help. And taking the average of that is nonsense. Whereas if we look at something like this, and in all the studies, it was essentially very, very close to 1.06, that tells us there's not a lot that you can do. Even if you had, cardiologists on staff at night, because some of the hospitals did, it's not really going to matter. So the question is, which of these three does it look like? The paper reported that I-square was 75%, and therefore heterogeneity was high. So I'm going to ask people by a show of hands, how many think it was A, B, or C? I-square is 75%, heterogeneity is high. How many think it's A? How many think it's B? How many think it's C? Okay, I usually get something like that. I usually get about 5% for A, 15% for B, and about 80% for C, and we're getting more or less that. I'm going to show you a second example. And this is called restrictive versus liberal transfusion. And in this case, what they were doing is when people are in a hospital, these are people with a particular type of illness, and many of them are going to need a transfusion, or a transfusion would help. The question is, do you use a liberal strategy, which means that as soon as they come to the hospital and you diagnose them, you do this transfusion immediately, or do you wait until they're extremely ill, and if it looks like they're going to die, you give the transfusion then? Why would you do one versus the other? Well, the reason for giving it immediately is that it might be more helpful. The reason for not giving it immediately is that for people who are this sick, the transfusion itself might kill them. So the question, on the other hand, the advantage of doing it later is that you don't subject them to the transfusion. You don't cause that additional risk unless you really have no choice. But the advantage is that you're not right. That's the advantage. The disadvantage is that by then it might be too sick. It might be too late to save them. So the question again is this: it turns out that the mean odds ratio was again very, very close to 1. On average, there was essentially no difference at all between them. But the question is again, what does the distribution look like? If it looks like this, then basically what we're saying is that the risk is always 50-50. Neither group is doing better than the other. On the other hand, if it looks like this, again, what we're seeing is that in some populations, using the conservative strategy, waiting as long as possible, is going to reduce the risk of death by 50%. And in other populations, it's going to increase the risk by 50%. Again, in which case, the average that we're seeing over here is simply the average of two opposites. It's not useful. What we really need to do is to figure out which patients fall over here and which patients fall over there. In this case, they reported that I-square is 29% and used that to classify the heterogeneity as being low. So again, by a show of hands, how many think it was A? Really? How many think it was B? How many think it was C? Okay, it turns out that in the first example, where we said that heterogeneity was I-square 75%, heterogeneity was high, it actually looks like this, okay? And in the second example, where we said that I-square was 29% and heterogeneity was low, it actually looks like this, okay? And the reason I showed this example is to sort of wake everybody up, because people often comment to this thinking that, I used I-square, other people use I-square, it's pretty common, it must make sense. I mean, to be completely honest, I chose this example to make a point. In general, it's true that when I-square is close to 0%, everything else being equal, you tend to have less heterogeneity. And again, everything else being equal and I-square approaching 1 tends to have more heterogeneity. But the point I wanted to make is that I-square does not tell you how much heterogeneity there is. It's telling you something else. If you actually want to know how much heterogeneity there is, you use the prediction interval, which is what I just showed you over here. For example, over here, if I tell you that the effects vary from 0.50 at one end to 1.5 at the other end, then you know exactly what the heterogeneity looks like. There's no confusion whatsoever. And similarly over here, if I tell you that the effects vary from, let's say, 0.95 at one end to 1.10 at the other, again, there's no confusion. Everybody knows exactly what it is. And that's the prediction interval. Okay, so I just to summarize these two, this was the case where I-square was reported as 75% and the heterogeneity was reported as high, and it looks like this. And here we have the transfusion analysis where I-square was 29%, heterogeneity was classified as low, and it looks like this. And to be clear, these are exactly on the same scale. Okay, so the question is, what's going on? Okay, so here, that was the introduction. Here's what I'm going to try to do in the time that we have. I'm going to make 5 points. Why we should not use I-square to quantify heterogeneity, how we should think about heterogeneity, and what I-square actually does tell us. Then at this point, everybody usually says, well, Michael, that's all very interesting, but I'd like to know what happened when you forgot your wedding anniversary. So I'm going to talk about that. And then finally, I'm going to make a point that I just added. I didn't used to say this, but after speaking with Waldemar a couple of times, and the topic sort of shifted, I want to talk about why I think that the way that we report heterogeneity actually shapes the way that we think about meta-analysis, and that shifting to prediction intervals will sort of change the framework of the way meta-analyses are used. So the first point, why we should not use I-square to quantify heterogeneity. Well, the answer is over here. You can see that it doesn't work. And even in a case where it does work, even if I say for the sake of argument that there was a lot of I-square was 80%, and there was a lot of heterogeneity, and if it actually turned out that it didn't look like this, but it looked like this. So in general, you could say it worked, but we still don't have any idea how much heterogeneity there is. Is it the case that at one extreme there's a risk ratio of 1.5, or is it possibly 2 or 3 or 4? I mean, saying that there's a lot of heterogeneity is not, you need something more informative than that. I mean, in medicine, we don't use terms, as I said before, like low, moderate, or high. We want to know what the numbers are. And so even in the case where I-square sort of works, it does not work well enough. Okay, so how should we think about heterogeneity? Well, the answer to this is so incredibly simple that it's almost embarrassing. What you should do is think about it exactly the same way that you do in a primary study. And all of us here have had a basic class in statistics. And in that class, we learned how to report heterogeneity in a primary study. And you can do essentially the same thing in a meta-analysis. So as a primary study, I'm going to use an example of kids. You go into a school, there are kids that are taking math. And you take some sample of those kids and you give them a math test. And then you look at the scores. And let's say we're talking about a test where the scores can go from 0 to 100. And after you do the sample, you do the analysis, the average score is 50. But we still need to know how did the effects vary. And the way that we would report this, and any first-year statistics student knows this, you're going to report the mean and the standard deviation. If we say that the mean is 50 and the standard deviation is 5, and we assume that the scores are normally distributed, you can figure that most kids, 95% of the kids, are going to score roughly in the range of 40 to 60. Why? Because if the scores are normally distributed, most kids are going to score in the range that begins with 2 standard deviations below the mean, up to 2 standard deviations above the mean. So 50, 2 standard deviations would be 10. The mean minus 2 standard deviations is 40. And plus 2 standard deviations is 60. Let's say that I report that the mean is 50 and the standard deviation is 10. By the same logic, I know that most kids are going to score between 30 and 70. And if I report that the mean is 50 and the standard deviation is 20, I know there are kids scoring as low as 10 and some scoring as high as 90. So essentially, by giving the reader the standard deviation, I've also given them the prediction interval. Because when somebody tells me that the mean is 50 and the standard deviation is 5, what I do with that in my head, almost without thinking, is I automatically compute the prediction interval, because the standard deviation by itself is not all that intuitive. But as soon as I hear that the standard deviation is 5, I automatically recognize that we're talking about this. And when I'm thinking about what the class looks like, I picture this in my head. And the same for this and for this. So the point that I'm making is that the standard deviation is really just a shortcut of how to report the prediction interval. I want to emphasize what I said before. Don't confuse the prediction interval with the confidence interval. In each case, we're able to report that the mean falls very close to 50, but that's entirely separate from how widely the scores are distributed. For example, if in this sample I had, maybe 20 kids, the confidence interval might look like this. If I had 100 kids, I would probably know the mean within plus or minus 1 point, because that depends on how many subjects I have in the sample. By contrast, the prediction interval depends on how widely the scores actually vary. If I'm talking about a class where most of the kids score between here and here, the prediction interval is going to look like this. And if I'm talking about a class where there are kids scoring as low as this and kids scoring as high as this, the prediction interval is going to look like this. So the confidence interval depends on how many people you have in the sample. The prediction interval depends on the reality of how kids actually vary in the class. Now, how do we talk about heterogeneity in a meta-analysis? Well, you can. This is a meta-analysis with 17 studies. And in each of those studies, they took adults who were suffering from ADHD, attention deficit hyperactivity disorder. These were randomized trials. Half of them were assigned to methylphenidate, such as Ritalin is a brand name, and half of them were assigned to placebo. And it turns out the average effect was 0.5 standard deviations. In other words, standardized mean difference is 0.5. This is real. The numbers happen to match almost exactly the numbers I was showing you for the fictional study, but this is a real analysis. It just works out the numbers are really easy to follow. So again, if I told you that the mean score in the meta-analysis was 0.5 and the standard deviation of scores was 0.05, then I would know that in the populations that are comparable to those in the meta-analysis, we're going to expect an effect between 0.40 and 0.60. The mean minus 2 standard deviations, the mean plus 2 standard deviations. If I told you that the mean was 0.5 and the standard deviation was 0.10, I'm looking at something like this. And if I told you that the mean was 0.5 and the standard deviation was 0.20, then 40 points below the mean gives me 0.10, and 40 points above the mean gives me 0.90. The reason, by the way, that that blue line is not quite at the bottom is that what we're trying to do is pick up 95% of the populations. If we went all the way out to here, we'd be picking up 99% of the populations. But it's like anything else. If you multiply it by 1.96, you get the 95% interval. If you multiply it by 2.58, I guess you get the 99% interval. I mean, it's not as simple as that. You might want to use the t adjustment as people here have written, but that's the basic idea. And again, I can report the standard deviation, or I can simply report the prediction interval. And if I reported the standard deviation was 0.05, people should intuitively understand that the prediction interval looks like this. But you don't actually need to report the standard deviation. The key point I want to take from this slide is that I can actually give you the prediction interval. I can say that in 95% of populations similar to these, the effect is going to fall between 0.4 and 0.6. And the reason that's important is that the idea of simply giving people the standard deviation only works for some effect sizes, such as the standardized difference in means. If you were working with a risk ratio or a log ratio, you'd have to do a transformation before actually doing the plus or minus 2 standard deviations. And while it's extremely easy to do, at that point, you've lost half of your audience. So what you can do, instead of giving the standard deviation, is simply report the prediction interval, because the standard deviation is only an interim step to getting there. The prediction interval is what people actually want. Okay, so to recap, in a primary study, we report the prediction interval, which is the mean plus or minus 2 standard deviations. Either we report it directly or we give the standard deviation, which allows people to figure it out for themselves. In a meta-analysis, we should similarly either report the prediction interval, or in some cases, you can simply give the standard deviation and people will figure it out for themselves. At this point, you people are very polite, but when I'm giving this in a less polite country, usually people have one of two reactions. Half of them say, well, obviously, you should give the prediction interval. You shouldn't be using I-square. Why do we come all the way down here and waste our morning on this nonsense? It's obvious. On the other hand, I get people that have been working with meta-analysis for a while. They say, it can't possibly be right. I mean, we've been using I-square all this time. If I-square doesn't work and the prediction interval does, and it's so simple, certainly people would be using it. You must be talking about something that you don't really know. So let me tell you what I-square actually does tell us, okay? And in order to do that, we need to provide some background. And I think most people here will have that background, but let me sort of run through it quickly. In a meta-analysis, you need to distinguish between the true effect size for a study and the observed effect size for a study. The true effect size is the effect size that we would see if we had a study that was infinitely large. So there was no sampling error at all. And we knew the effect size for that population precisely. That's the true effect size. The observed effect size is the effect size that we see in our sample and put into the forest plot. The key is that the dispersion of the observed effects tends to be greater, wider than the dispersion of the true effects. Why is that? Well, imagine a study where imagine a meta-analysis where all of the studies are actually estimating exactly the same parameter. What kind of a study would that be? Well, imagine that there's a drug company which needs to test the efficacy of a drug, and they run 5 studies which are all exactly the same. They're all random samples from the same population. They all use exactly the same medication. They all measure the outcome in exactly the same way. So each of those studies is estimating the mean effect in that particular population, right? And therefore, the true effect size for all of these studies is the same. Remember, the true effect size is not the effect size for the 50 people in the sample. The true effect size is the true effect size for the 1,000 people that were in that population that they're drawing from. So by definition, the true effect size is the same for all studies. And I've indicated that here by using red circles. So all 5 studies have the same true effect size. Would we expect the observed effects to look like this? Well, obviously not. The whole reason that we do statistics, the whole reason there's a job for people like us, is that if the true effect size is over here in any single study, the observed effect is in half the cases, it's going to be lower than that. And in half the cases, it's going to be higher than that. I don't know if the people here know Alex Sutton from University of Leicester. Okay, so Alex once said to me, we were chatting about this, or maybe he was giving a talk, and he said, if the 5 observed effects look like this, we would assume that money had changed hands, which I always thought was a lovely expression. This is ChatGPT, by the way. If you have too much time on your hands, you get stuff like this. Rather, if you did 5 studies, they might look like this. So this is actually, you know, the mean of the true effect size. You get a couple that are lower and a couple that are higher, or they might look like this, or they might even look like this. And you'll notice that it might look like this if all the studies are large enough, so they have only a relatively small amount of error. And the confidence interval, which tells you how precisely we know the mean, in all cases overlaps the true mean. So this one, you know, it's certainly possible you're going to get a study where the effect is over here, but the confidence interval includes the mean. And at this extreme, again, the effect is over here, but the confidence interval includes the mean. On the other hand, if you had something like this, where the studies were smaller, and therefore each one of them had a lot of error, they might be spread out much further, but still every confidence interval includes the mean. See, this includes the mean and this includes the mean. So if you did this a different way, if you simply drew the confidence interval around the mean, another way of thinking of that is that each of the studies would fall within the range of the confidence interval, or I guess the range of the error bar for the actual mean. So basically the idea is the larger the studies are, the more precise you expect every one of these studies to be, and the observed effects will tend to fall reasonably close to the true effect. But when you get studies that are small, the individual effects, the observed effects might fall some distance from the true effect. So in other words, what I'm saying is that it's possible to get a distribution of observed effects that looks like this, or like this, or like this, while the true effects actually look like this. So the basic idea I'm trying to convey is that the dispersion of observed effects tends to be greater than the dispersion of true effects. That's very clear in this example, because in this example, the true effects have no dispersion at all, and the observed effects obviously do have dispersion. So by definition, the observed effects vary more than the true effects. But the same idea holds true when the true effects do vary. If the true effects vary this much, it's likely that the observed effects will vary more. How much more depends again on the size of the studies. If the studies are large, probably vary a little bit more. If the studies are small, might vary a lot more. So in a case like this, where all of the confidence intervals overlap the same number. You see, these all overlap this. If we wanted to estimate how much heterogeneity there is, we'd estimate it as 0. Why? Because the effects vary this much, and we would expect them to vary this much just based on how much error there was in each study. On the other hand, if it looked like this, you see now the effects fall along in the same squares. The effect size has not changed, but what has changed is now each study is more precise. If the studies were this precise, we would not expect that the effects would vary this much if there actually was no heterogeneity. And therefore, we figure out how much heterogeneity we would expect based on error, how much we're actually seeing, and the difference gives us the amount of heterogeneity that actually exists. It's not simply due to sampling error. I'm going to show the same exact thing over here using these distributions. The distribution is something that I think is a good way of presenting the prediction interval. The prediction interval is simply the two ends of this, but you get a sense of, all of the whole normal distribution. So if the observed effects look like this, the true effects might look like this. This would be the case if all of the studies were reasonably large, so there was only a small amount of sampling error, and most of what we're seeing is true. Or they might look like this. In this case, only a portion of what we're seeing is true. Or they might look like this. In other words, if you had studies that varied from here to here, but each of them had so much error that just based on the error, we would expect to see this much this much dispersion, then it might turn out that the true effects only vary like this. And in the extreme case, you might have effects that vary from here to here, but all of that can be explained by sampling error because all of the studies are small, in which case the true effects actually, as far as the evidence suggests, are exactly the same. In this case, heterogeneity would be estimated as 0. The variance of true effects is designated tau squared. The way that the variance of observed effects is going to be equal to tau squared plus the variance attributed to error, right? So it's basically, if you want to figure out how much the observed effects are going to vary, you start with the variance of true effects, and you add to that whatever variance is added just due to sampling error. And then the way that we compute the tau squared, the way that we estimate it, is we start with the variance of observed effects, which we can compute the same way you would in a primary study. You remove the portion of that you think is attributed to sampling error, which basically depends on the size of the studies, and you're left with your best estimate of tau squared. That's a very simple version of it, but it's accurate. So in this case, now that we have the dispersion of observed effects, and we have the dispersion of true effects, a reasonable question to ask is what's the relationship between the two of them, right? We're looking at the observed effects. We're interested in the dispersion of true effects. If we're looking at the observed effects, what proportion of that is due to true effects? It's a very reasonable question. And that value is I squared. The formula that we generally see for I squared is Q minus DF over Q, which is not necessarily intuitive, but it can be translated conceptually, at least, to the variance of true effects over the variance of observed effects. Or another way to say that is tau squared over the total variance, basically true to total. And in this case, that would mean the ratio of the red line to the blue line. So if I took a line, which I actually did last night using PowerPoint and measure the lines, if I take a line and draw it from here to here, and then I take another line and draw it from here to here, the ratio of those two is going to be the ratio of true to total in linear effects. And if I square that, I'm going to get the ratio of true to total in squared values, which is going to be I squared. So in this case, I squared is 46%. I know people are surprised. They think, well, this is not 46%. This is more like 70%. But again, when you're looking at this as a person, you're using linear units, and I squared is dealing with the squared units. So if you could think about this as squared, so you have a whole sphere rather than a line, the ratio of inner to outer would be 46%. In this case, I squared is 12%. In this case, I squared is 3%. Okay, and in this case, if there's no variation, in other words, after we do our imputations, it turns out that we estimate that there's no heterogeneity at all, then I squared has to be 0% because it's the ratio of 0 to something. Now, here's the thing. I just showed you an example over here, where in this case, I squared was 46, and I squared was 12, and I squared was 3. And there appears to be a pretty solid relationship between I square and the amount of heterogeneity. So you might wonder, how is it that, in those examples I showed you earlier, there was such a disparity? Well, the answer is this. If we're dealing with a situation where all of the observed effects are the same, then indeed there would be a very strong correlation between I square and the amount of heterogeneity. However, that's not necessarily the case. Suppose I tell you that I square is 50%. If the observed effects look like this, and I square is 50%, the true effects would look like this. If the observed effects look like this, and I square is 50%, the true effects would look like this. And if the observed effects look like this, and I square was 50%, the true effects would look like this. So simply telling you that I square is 50% doesn't actually tell you whether we're talking about this or this or this. And so for the sake of argument, if people that reported I square actually showed you the forest plot and they said, half of this is real, then it would have much more validity than the way people actually do it, which is simply presented in the abstract. Although even then, as you see from here, most people, including myself, don't really have a sense of what 3% of this is. I would have thought it's much less than this, but it isn't. Okay, so the idea of using I square to tell you how much heterogeneity there is generally breaks down because of exactly this reason, except in the case where I square is 0. Now, I think this is probably sort of the heart of the talk. Once you understand that we're talking about observed effects on the one hand and true effects on the other, you recognize that there are 3 distinct questions we can be asking. If you're dealing with a primary study, in a primary study, of course, it's also possible to break it down into true effect and observed effects. If each student, for example, is measured at multiple points in time, and then we take the average of those to get the true effect, and we see how much deviation there is from each measurement, versus we can calculate the within study error and the between study variance. So the concept exists over there. I give you an example where we weren't using it. But in general, when people think of a primary study, they essentially think of the observed effect as being the same as the true effect. So the only question logically they can ask is how much do the effects vary? By contrast, in a meta-analysis, where we make a clear distinction between true and observed, there are 3 distinct questions that we can ask. One question we can ask is, do the effects vary at all? Okay? In other words, I'm looking at the blue line, but is it possible that the true effects look like the red line? They're all exactly the same. I think it's a silly question because if you're pulling studies from the literature, the effects will vary. There's no situation where you're testing a drug and you're going to get exactly the same effect with all the people. But whenever people report the Q value and the P value, that is the null hypothesis that they're testing. A second question you can ask is, of the variance that I'm seeing, what proportion is real? I see a blue line that looks like this. I'm interested in the red line. What's the ratio of the two? And that is the domain of I squared. But I would say in 99.9% of cases, when a researcher or a clinician says, how much does the effect vary? What they're asking is this: what is the actual range of effects? And in this case, you'd report that it goes from whatever that number is at the bottom left to the number at the bottom right. And what's ironic is that you can simply report this, which is so clear and intuitive. When somebody reports I squared, they're starting with this and making it more complicated by putting in another line and then asking about the ratio between them. And that's really not the major part of the problem. The major part of the problem is that when somebody reports the ratio, people interpret it as though it's this, and it isn't. These are 3 valid questions. You can ask, is there evidence that the effects vary at all? You can ask what's the ratio of true to total, and you can ask how much the true effects actually vary. Each is a valid question, but they are not interchangeable. Right? If you ask how much do the effects vary, and somebody gives you the proportion of what you see that's true, those are 2 entirely different questions. Okay, at this point, as I said before, people usually want to know what happened when I forgot my wedding anniversary. The story that I'm going to tell you is true. The names have been changed to protect the innocent. No, that was the beginning of a television show about police we used to have on in the United States called Dragnet. This is actually a true story. Now, I asked ChatGPT, because again, I had too much time on my hands, to draw a picture of somebody that forgot their wedding anniversary, and he looked like this. Then I asked ChatGPT to draw a picture of a statistician who forgot his wedding anniversary, and it looks like this. I'm going to send him a letter of complaint. But in any event, I said to my wife, what can I do to make this right? And she said, well, you can go down to Neiman Marcus. The people there are expecting you. And so Neiman Marcus is a department store, a very expensive department store in the United States. So I went down there, and there actually was a woman. She said, "Oh, yes, so-and-so is waiting for you." I went over there. I said, "I have no idea where to start." She said, "Well, your wife pointed out these pearls. We actually have them saved here in a desk until you come in." And then she said to me, "And because your wife is such a nice person, we're going to give you a discount." Okay. So there are three questions. And all of that is true. There are three questions I could have asked the salesperson. I could ask her, is the cost zero? In other words, is it free? Okay. It's a valid question, but if I ask that question, they're probably going to call the security guard and have me sort of walked out of the building. It's a question that's valid, but I'm not going to ask that because I already know the answer to it. A second question I can ask is, well, you said I'm going to get a discount. What proportion do I actually pay? In other words, whatever amount most people pay, what proportion of that am I going to pay? So if most people pay some amount, I'll pay 50% of that for the sake of argument. And this is actually what she did. She didn't tell me the price. She told me how much of a discount I was getting. And the reason for that, it turns out, is because if you tell somebody the price up front, they tend to fall over. They're going to sort of ease you into it slowly. So the second question I can ask is, what's the proportion? The third question I can ask, which is the question I asked originally, and the only thing I really cared about, how much do I pay? Right? That's the thing that I want to know. And in this case, she told me the amount. Okay. It was, for the sake of argument, let's say it was $5,000. Okay. So again, which do we want to know? There are three questions. This seems to me to be an excellent analogy between what's going on here, what's going on with I-square. One question I can ask in the case of a meta-analysis is, do the effects vary at all? And by analogy, I could have asked this very nice woman, can I get this for free? But I already know the answer to both of these, and therefore there's no point asking them. A second question that I can ask in the case of I-square is, of the variance that I'm seeing, what proportion is real? And similarly, I could have asked the salesperson, of the price that's listed here, what proportion do I need to pay? It actually is an interesting question. I mean, I'd like to feel that I'm getting a discount. I mean, assuming that I believe what she's going to tell me, I'd like to feel that most people, those idiots are paying this much, but I, because my wife is so nice, is going to pay less. So it's an interesting question, but it still doesn't give me the answer that I need. On the other hand, I can say how much, in the case of a meta-analysis, how much did the true effects vary? And in the case of this jewelry, I could say, well, how much do I need to pay? And that, again, is a valid question, but that's the only thing that I really care about. Okay? Now, here's where this example, I think, becomes important. There's a critical difference between the two cases. If I said to the salesperson, how much do I pay? And she said 50%, I'm not going to write out a check to Neiman Marcus for 50%. Because I know, again, the security guard that didn't chase me out of the store before is certainly going to do it now. You can't write a check for a percentage. It doesn't make any sense. By contrast, because we know, okay, she told me I'm paying 50%. So I know that if the regular cost was $100, I'm going to be paying 50. If the regular cost was $1,000, I'm going to be paying 500. And if the regular cost was 10,000, I'm going to be paying 5,000. So I can't simply write a check for 50%. And simply knowing that it's 50% does not allow me to compute which of these I need to pay because I don't know what the regular cost was. By contrast, if I'm talking to a statistician or to a researcher or to a clinician, and I say to her, what is the range of effects? And she says 50%, most people will accept that. In other words, if she say it's 50%, most people will assume it looks something like this, because they have some idea in their head of what 50% looks like, when in fact, it could just as easily be this or this. So in the case of writing the check, just as a normal consumer, I'm not going to accept 50%. There's no, and by the same logic, if somebody tells me what I-square is, I should not accept that as telling me how much the effects vary, and yet everybody does. Now, most computer programs now have the option of reporting the prediction interval. Stata introduced that. Metaphor, the program by Wolfgang Buchbauer, introduced it. And comprehensive meta-analysis, and I should point out that that's actually our program when we get money when you buy it, so that's full disclosure, does it, and also computes that whole curve that I was showing you before. So it's very easy to do. Just as it's easy to get the confidence interval, it's also easy to get the prediction interval. The problem is people don't take advantage of that. Going back to those two examples I showed you earlier, in the off-hour presentation, we said that I-square was 75% and the heterogeneity was high and it looked like this. The reason is that the fact that I squared is 75%, if the observed effects look like this, then the true effects would look like this. 75% of this is this. If the observed effects look like this, 75% would give you this. And if the observed effects look like this, 75% would give you this. As it turns out, the observed effects actually look like this, and 75% of that is this. And here is the actual forest plot. If you look at that, look at how narrowly the observed effects are clustered. In fact, they're so narrow that in a couple of the cases, you can't even see the observed effect. It just merges with the anchor. I mean, look at all of these fall within a very, very small range of I guess it was 1.06. If we take 7, so that's the variation of the observed effects, which looks like this. If you take 75% of that, because 75% of the dispersion is real, 75% of a tiny amount is still a tiny amount. Okay? By contrast, if we go to the transfusion analysis, where we said that only 29% of what we saw was real, but and that was mistakenly said heterogeneity is low, it actually looks like this again. If the observed effects looked like this, 29% of that would have given me this. If it looked like this, 29% would have given me this. And if it looks like this, 29% of that would have looked like this. As it turns out, the observed effects vary a lot, and 29% of a huge number is still a pretty large number. And again, this is all on the same scale, remember. Look at how the observed effects varied over here. They start all the way down at the bottom at around 0.5 and go up to around 3.2. So 29% of this still gives us this. And as I said before, I picked up these particular examples to make a point, but I didn't have to look very far to get these examples. I did this in BMJ, I did it in epidemiology, I did it in a half a dozen other fields, and in each case, it took me about 5 minutes to get an example that looked like this. So the comparison of the two is that this is the off-hours analysis, very small amount of variation in the observed effects, 75% of that gives me this. In the transfusion analysis, a tremendous amount of variation in the observed effects, 29% of that gives me this. And as I said before, it's not just I-squared. As soon as the people in each case, and I simply picked up words that they used in describing their findings. These people described the heterogeneity as high, and in point of fact, that's misleading. It's clearly incorrect. And these people described it as low, which again is clearly incorrect. So you see where that kind of a thing leads. By contrast, imagine what would have happened if they simply reported the prediction interval, which can be sent out by a computer as easily as I-squared. If I told you that the effects here, the true effects, are all expected to fall in the range of 0.96 to 1.17, then you know exactly how widely they vary. And if I told you over here that the true effects are all expected to fall in the range of 0.56 to 1.63, there's no confusion about that. I mean, if you want to go ahead after that and talk about from a clinical point of view, whether you think this is small, moderate, or large, have at it, that's perfectly okay. But first, we're presenting the actual numbers the same as we do for the mean or the confidence interval. And then you can try to think about, you can have your opinion of the clinical impact, and the reader can agree with you or disagree with you, but at least you're all working with a common set of numbers. Okay, as I said before, the two examples that I used are not typical. It's true that all things being equal, when I-squared is near zero, there's generally a relatively small amount of variance. And on the other hand, when I-squared is high, but when I-squared is high, the amount of variance can be almost anything. It might be this, it might be this, it might be this. I don't have a scale over here, but that's part of the point. There's no scale involved. It can be almost anything. If you're talking about, for example, the proportion of people that die after a procedure, and we say that I-squared was high, the top value over there might be 20%, might be 50%, might be 90%. And you'd call that a lot. You might have an I-squared of 75 for all of them. But it's critical to know which one of these we're talking about. Okay, this is not a difficult concept. I mean, sometimes I'm afraid that if you bring people together in a room like this to talk for an hour and a half or 2 hours about I-squared, the people think there must be some kind of a complicated concept that we're talking about over here, and there's a need to sort of have a discussion about it. The only reason we need to have a discussion about it is because so many people use it incorrectly. If you were new to meta-analysis and we didn't have this whole history of I-squared, I wouldn't need to discuss it at all. It's a question that wouldn't even, it's an index that wouldn't even occur to anybody or wouldn't occur to most people. When people ask about how much heterogeneity there is, they're all asking for the prediction interval. And the idea of, everything we've been talking about over here, it's not more complicated than it seems. If it seems to you that this is a very simple concept, it's a proportion, it is. Okay, so at this point, the question is seriously. In other words, I mean, am I crazy? Okay, so I was teaching the class in a workshop in London about 7 or 8 years ago, and I gave, the same sort of lecture I'm giving over here, and the fellow who was sitting just about where you're sitting stood up and started screaming at me. He said, "You're an idiot. You know nothing about meta-analysis. You have no right to be teaching this class," and he stormed out of the room. Okay, it was a 3-day workshop. The next day he had settled down, he came back, and Julian Higgins, who's one of the 2 people that created I-Square, was in town for a meeting. And he, just as a friend, he stopped by. He was sitting, I asked him to sit all the way in the back. Everybody came in, and I asked this fellow to voice his objections again. He was more than happy to do that. He said, "You're an idiot." I said, "Okay, but instead of screaming at me, why don't you scream at Julian? Because he's the person that..." And Julian was kind enough to let me record that and to use it in situations like this. I'm going to show you what happened. I've been teaching this class for a while, and I come up with a lot of outrageous things, some bad jokes. People put up with most of it. But one thing that I constantly get pushback on is that people say that I have to be making a mistake in discussing I-Square, because if you look in the literature, and people here who are familiar with, who have read meta-analyses are probably familiar that there are, literally hundreds of meta-analyses out there where people say, if I-Square was 75%, that means that I have a lot of dispersion. And whereas, as I said yesterday, it's generally true, there is a correspondence. The higher, everything else being equal, a higher value of I-Square will correspond with a greater amount of dispersion. But I-Square really doesn't tell you how much dispersion there is. Because when we say, there's a lot of dispersion, what does that mean? When we're talking about a lot of dispersion, we're talking about this on a clinical or a substantive scale, whereas I-Square is not, it's not on the same scale. It's on a scale of proportions. It tells you what proportion of what it is that you're looking at is probably real. And so it really was not intended to answer that question. It was intended for a very specific purpose, which is to say, of the variance that we're looking at, how much of that is probably will reflect variation in true effects rather than the sampling error. It's an incredibly important function. As I showed yesterday, if you take the variation that you're looking at and multiply that by I-Square, you get the variation of true effects. But that's the way it was intended to be used. And when people say, well, I-Square is 75%, and therefore that means there's a lot of variation, a lot of clinical variation, a lot of substantive variation. It's not the way I-Square was intended to be used. So what I started to say is that I often get a lot of pushback on this. People who are taking the course, they sort of grab me at lunch or at night and they say, you have no idea what you're talking about. You have no right to say that. I've published papers, and I know what and therefore, and I teach a class, and I know what I'm talking about. So it occurred to me, I wanted to share this clip with you. This is a clip from a Woody Allen film called Annie Hall. And let's see. I just want to set this up. He's waiting online to see The Sorrow and the Pity, together with his girlfriend Diane Keaton, and they've just finished having an argument about sex, and now they're arguing about Marshall McLuhan. And the fellow behind him is pontificating about. Marshall McLuhan was a famous writer in the 60s.
It's the influence of television. Yeah, now, Marshall McLuhan deals with it in terms of it being a high intensity, you understand? A hot medium.
What I wouldn't give for a large sock with horse manure in it.
Which he uses essentially
What do you do when you get stuck on a movie line with a guy like this behind you?
Wait a minute, why can't I give my opinion? It's a free country.
He can give you. Do you have to give it so loud? I mean, aren't you ashamed to pontificate like that? And the funny part of it is, Marshall McLuhan, you don't know anything about Marshall McLuhan's work.
Really? I happen to teach a class at Columbia called TV, Media, and Culture. So I think that my insights into Mr. McLuhan, well, have a great deal of validity.
Oh, do you?
Yeah.
Well, that's funny because I happen to have Mr. McLuhan right here. So yeah, just let me come over here a second.
Oh,
Tell him.
I heard what you were saying. You know nothing of my work. You mean my whole fallacy is wrong. How you ever got to teach a course in anything is totally amazing.
Boy, if life were only like this.
Okay, so anyway, when I saw that, I thought, wouldn't it be nice, if life was actually like this? So what I have over here in the back is Julian Higgins, the creator of I
Good morning.
Okay. Oh, stand over here. Okay.
Gifts too.
Yes, no, come over here. Yeah. You're good. Okay. Yell at him, not at me.
So, you want me to say something? Basically, Michael is right. And we always portrayed it. I squared, I see it largely as a measure of the extent to which studies agree with each other. And that doesn't matter what their actual results are. And in fact, when we conceived I squared, we were looking at forest plots, much like the one you had, and we have multiple forest plots. We said, well, there's something I can see in that without looking at the scale or anything else. It's about the extent to which the confidence intervals overlap. And we want a measure that reflects that. And, by the whole notion that we can use I squared for risk differences, for odds ratios, for differences in means, for prevalences, almost itself argues that it doesn't tell you anything about the actual scale, the actual numbers coming from the studies or underlying the studies. So I just want, Michael, I know, we have 11,000 citations of the paper. Most of them are using it inappropriately, sadly. But don't stop citing it. Just use it appropriately.
For about half an hour, we don't have enough time to show you the whole thing. But I want to point out two things that are particularly important. First of all, he said, basically, Michael is right. Okay. And the second thing he said is the fact that it can be used with any index tells us that it does not give us the actual value, right? It's a simple concept. I was just concerned. The only thing you really know about me so far is that I can't even remember my own wedding anniversary. So I wanted some backup that I'm not the only person that says this. In fact, we've published quite a few papers about this, and Julian was a co-author on many of them. There's no daylight between us on this. We both feel exactly the same way. And the first time I ever came to him and asked him to write a paper about this, he said, I've been talking myself blue in the face for years, giving lectures, explaining that people are misusing it, and I need to move on to other parts of research. He said, if you write a paper, I'd be happy to co-author it. And that's how we sort of got started. It's also in our textbook, all of this, which he co-wrote with me. So I'm not saying anything radical over here. I'm simply pointing out something which is obvious. Now, the way that this whole lecture got started was Waldemar was speaking to me, and he said he wanted to impress on people the idea that when you report the results of the meta-analysis, it's not simply the mean or the confidence interval or the prediction interval. It really comes down to providing people with an understanding of the potential utility of the intervention. And then we sort of worked our way back to prediction intervals, which is a critical part of that. I want to give you an example over here of why it's so important to report the prediction intervals. This is an example called tocilizumab for COVID-19. This was a meta-analysis that was published during the pandemic. It was published in the Journal of Medical Virology. And what happened over here was this. All of the studies, I think there were 23 studies, where patients who were admitted to a hospital with COVID-19, these are observational studies. Some of them were given a drug called tocilizumab, and some of them, plus the standard procedures, and some of them were given the standard procedures, but were not given this drug. So we're looking at potential impact, although it's observational, of tocilizumab versus a placebo. And as I said, there were 23 studies. This is from the abstract and also from the conclusion. A total of 23 studies with 6,200 patients, 1,900 in the tocilizumab group and 4,300 in the standard of care group were included. Look at the part that's underlined. The overall mortality was lower in the treated group compared to the standard group. The risk difference was minus 0.06, 6 percentage points. The confidence interval, minus 0.12 to minus 0.01. It excludes 0. And the p-value was 0.03. Okay? And then they conclude Okay, that's the key point. The risk difference favors the drug, and it is statistically significant. Heterogeneity was evaluated using the I-square statistic as defined in the Cochrane Handbook. I-square values of more than 50% were considered substantial heterogeneity. So they reported that on average, this works, but there is substantial heterogeneity. They never go on to say what that means. Okay, they did go ahead and do subgroup analyses and so on, but this is their main point, that the mean is statistically significant, but substantial heterogeneity, it doesn't tell you how much there is or what the actual range is. I'm going to open this up in CMA. Let's see if I can do that. So I'm going to say, okay, this is the tocilizumab analysis. The way this works in CMA, since these are 2x2 studies, you simply enter the study names. In each study, you enter the total number and the number that died, and it automatically computes the odds ratio and the risk difference. In this case, they're using the risk difference, so that's what I'm going to use. I run the analysis. I'm going to sort this from low to high so we can get some kind of a sense of it. And down here, you have the prediction interval. And what that tells you is that at one extreme, there are some populations where this reduces the risk of death by 30%. But at the other extreme, there are some populations where, I shouldn't say reduces, where there are some populations where it's associated with a 30-point drop in the risk of death. And in some cases, in some populations, it's associated with an 18-point increase in the risk of death. And to see that more clearly, I can plot this. And so over here, this 0 would be the null point. The reason it's statistically significant is that the confidence interval doesn't include 0. Remember, statistical significance only has to do with the mean. But what we see over here, if you can think of an imaginary line going up and down over here, in roughly 30 or 35% of the populations, it actually increases the risk of death, right? And if you're looking at this, and the only thing that you see is that it's statistically significant on the positive side, and there's substantial heterogeneity, and who knows what that means, then most people would say, well, I'm going to use this. It's proven to be helpful, when in fact you might be increasing the risk of death for 30% to 35% of the people that you're treating. Okay, and I'm convinced that very few people that read the paper were able to understand this. Something else that CMA will do, and I wasn't going to show this, but Waldemar, you said it probably would be helpful, is that it actually creates a report that explains what each of these numbers means. So basically over here, it says the I-square statistic is 81%, which tells us that roughly 81% of the variance in observed effects reflects variance in true effects rather than sampling error. And if you click this little button over here that says notes on, it annotates it to say, in this case, notes on I-squared. There's a common belief that I-squared tells us how much the effect size varies. In some cases, I-squared values have been employed to classify the amount of variation as being low, moderate, or high. While this interpretation of I-squared is ubiquitous in some fields, it's nevertheless incorrect. I-squared is a proportion, not an absolute amount, the same point that Julian was making. It tells us what proportion of the variance in observed effects reflects variance in true effects rather than sampling error. It does not tell us how much the effects actually vary. And finally, over here, the statistic that tells us how much the effect size varies is the prediction interval, which is discussed below. And then over here, we have a whole section on the prediction interval. If we assume that the true effects are normally distributed, we can estimate the prediction interval is minus 0.30 to plus 0.18. The true effect size in 95% of all comparable populations falls in this interval. And then notes on the prediction interval. The prediction interval will be accurate if all relevant assumptions are met. However, if our estimate of the mean is incorrect, if our estimate of the standard deviation is incorrect, and or the effects do not follow a normal distribution, the interval may be misleading. And then I go on to discuss various other things. The idea of that is that researchers who don't know meta-analysis well will read that. They will begin to understand what their statistics actually tell them, and then they'll be able to write a results section and a discussion section that actually mirrors what they saw in the data. What I see now, and I review many meta-analyses, people always get the statistics right because they're generated by the computer, but then they misinterpret them. So they'll get, for example, I-square and then misinterpret what it actually means. This is meant kind of as a teaching tool to help people get it right. So let me come back over here. And I'm going to come back over here. Okay, this was just pictures of what was going on in CMA. Here's where we entered the data. Here's where we analyzed the data. Down here, you can see the confidence interval a little bit more clearly. So this is the, I'm sorry, you can see the prediction interval a little bit more clearly. Here's the confidence interval, which, by the way, people often misinterpret the confidence interval. They think that that tells us how wide the effect size varies, when it does not. It simply tells us how precisely we've estimated the mean. And here you can see the prediction interval, and here you actually have the line of nil effect, and you can see that roughly 30% of the studies fall on the right side of that. One thing I mentioned, and this is simply the same plot you saw a minute ago, one of the things you can do is to annotate it. Hannah pointed this out to me, one of my collaborators, is that I keep emphasizing the fact that there are many, that if we simply say there's substantial heterogeneity, we're completely missing the point that in roughly a third of the cases, there might be damage. We also are missing the fact that in some cases, this might reduce the risk of death by as much as 30 percentage points, right? We're focusing on the mean, which is a 6 percentage point decrease in the risk of death, which is not as large as we might like. If we have nothing else, we might still want to use it. But there actually are cases where it might be a first line of defense. So if we can, the next thing to do, by the way, would be to break this down into subgroups and see what cases look like the ones on the right and what cases look like the ones on the left. Critically, we don't know to do that until we first see how much heterogeneity there is and what it looks like. And okay, this was again with the help of GPT. What I'm suggesting is that if you have a group of clinicians sitting around the table and trying to decide whether or not to use it, based on the fact that the mean is statistically significant and there's substantial heterogeneity, I'm going to bet that very few of them actually know that the distribution of effects looks like this. What I wanted to show you, going back to the point that you made, is how this would affect our ability to actually use this drug. This is the same plot we saw a minute ago, and I'm going to assume, for the sake of argument, you can put in any numbers that you like, that an effect size where if it reduces the risk of death by 10 percentage points or more, that would be considered a clinically useful effect, because there maybe are other protocols which already can reduce the risk of death by up to 10%. So anything greater than 10% would be clinically helpful, and anything less than 0 would be clinically harmful, because you don't want to increase the risk of death at all. So basically, looking at all the studies, we get about, let's say, 40% where it's helpful, and roughly 35% where it's harmful. So there's really no reason to use it or not, and so you'd probably avoid it. However, if you break this down, and you can do this in CMA, break it down into subgroups, and run an analysis only for the non-severe patients. Now, all of these people are in the hospital, but some of them, have a very small chance of living, and some of them have a greater chance of living. If you do it only for the people that are moderately, that are not in the worst possible shape, the ones that are less severe, and now the curve looks like this. So it's going to be helpful for maybe 5% of them, but it's going to be harmful for about 60%. By contrast, if you look at the patients that are extremely ill, it's going to be helpful for roughly 60% and harmful for only about 5%. So you see, once you have something like this, if you then know that you need to pursue it, you might end up with something like this, where you actually know that in these patients you can't use it, and in these patients you can. And they did actually do subgroup analyses. They found things that are similar, but they never presented it in a way that makes it this clear. Okay, a couple of technical points. As I mentioned before, when you're computing a prediction interval, in many cases you actually need to transform the data. You can't simply take the mean plus or minus 2 standard deviations until you put it into the correct metric. And so that's one of the reasons you want to use a computer program to do it. Also, you want to adjust for imprecision. If you actually knew the mean and you knew the standard deviation, then you could do the mean plus or minus 1.96 standard deviations. When you're working with primary studies, that's generally what people do, because in most cases, a primary study will have at least 30 people in it, and therefore your estimates of the mean and standard deviation are reasonably precise, and therefore you can do that. In a meta-analysis, you might be working with a much smaller number of studies, and therefore we want to expand the interval so that in case the standard deviation is larger than the number we're using, it will take account of that. And in case the mean is lower than the mean we're using or higher, it'll take account of that. So it expands the interval. The impact of that, if you have at least 10 studies in the analysis, with 17 studies, it will expand the interval by around 10%. It depends on a lot of things, but that would be a sort of a reasonable number to think about. If you have only 5 studies, it might expand it by a very substantial amount, in which case it's not really informative anymore. So I don't think it's really useful to report a prediction interval unless you have at least 10 studies. Let me rephrase that. If you have a situation where you expect the effects to all fall within a very narrow range, and the chi-square, the variation is estimated as being very small, then it might be okay to report the prediction interval and say that the effects appear to fall in a fairly narrow range. But once you're talking about a situation where the effects vary, you believe they're going to vary based on theory, and or you get a high estimate of variation, at that point, unless you have 10 studies or more, the estimate of the prediction interval is going to be so inaccurate, it's probably better off not to report it. Also, when you're computing the interval, it's going to be the mean plus or minus some number that assumes that these effects are normally distributed about the mean. So one thing I always do, and especially in a situation like this, where it turns out that we have some studies on one side of the nil and some studies on the other, is I want to go back and make sure that there actually is data that supports this. So in this case, based on that, since the mean is over here and it's forcing it to be normal, it might have pushed this over the nil, even though there are no studies that actually show that. So in this case, I went back. It turns out there are 1, 2, 3, 4 studies that show harm, and they are statistically significant. And in fact, if you look at the other side, there are 1, 2, 3, 4, 5, 6, 7, 8 studies, 9 perhaps, that show harm and that show benefit and are statistically significant. So we have a ratio of about 2 to 1 of studies that actually show clearly that it's helpful or it's harmful, which is also the ratio we found in that curve. And so we know that this part of the curve is not simply an artifact of the fact that we're trying to make it normal. It actually is backed up by the data. Okay, and I think that's very, very important. One thing I wanted to mention is that when we talk about the prediction interval being imprecise, if you have a small number of cases, people say, well, in that case, I might as well go back and use I-square. The fact of the matter is they're all based on exactly the same numbers. They all start with Q and the degrees of freedom. We use that to estimate chi-square. We use it to estimate I-square. We use it to estimate the prediction interval. So to the extent that the prediction interval is imprecise, I-square is going to be imprecise by the same amount. However, I think it's much more important to get it right when you're talking about the prediction interval. And the reason is that if you report, let's say I-square is supposed to be 75%, and you report that it's 50%, you really haven't done any harm because people have no idea what it means anyway, right? I mean, so what's, however, if you report that the prediction interval is here to here, it actually should be here to here, you've done a substantial amount of harm because people know what it means and therefore they're going to be using it. Okay, I guess this is my last topic before we get to questions and answers. The way we report heterogeneity shapes the way that we think about meta-analysis. So the implication of using I-square and not using the prediction interval is that researchers who report I-square don't actually know what the range of effects looks like. And then when they write the discussion, they know what the mean is. They don't really know how much heterogeneity there is or what the range of actual values is. So what they tend to do is they'll say something in the beginning that first they'll explain how they computed heterogeneity by copying and pasting from 1,000 other papers that have been written. And then they essentially ignore it for the rest of the paper. They might mention that it was substantial or large. And when they're talking about the utility of the intervention, they never come back to it again. They focus on the mean and whether or not the mean is statistically significant because that's something they understand. But they don't really know heterogeneity, and therefore it's essentially not a factor when they're thinking about the utility of the intervention. If you have terms like none, low, moderate, substantial, considerable, significant, these terms are not really informative. So there are 3 reasons that I would not use these terms, that I think these should basically be put away, certainly not if they're based on I-square. The first reason is that they're based on I-square, and as we saw before, I-square does not tell you how much variation there is. So any term that's based on I-square, by definition, can't possibly be useful for describing the amount of heterogeneity. The second reason I think we should avoid these things is that they don't take account of the mean effect. So let's say, for the sake of argument, you reported that the amount of heterogeneity was considerable. And let's say that we all had a common understanding that considerable means this. And let's assume that that was actually based on tau or tau square, so it actually is correct. When you're reporting the mean over here and you're reporting heterogeneity separately, it does not allow you to distinguish between this and this, which from a clinical point of view is a very important distinction. And the third reason is that, again, even if you were using an index that actually is tied to the scale, so it actually does tell you how much heterogeneity there is. But when people report that the amount of heterogeneity is small or large, let's say I said to you over here, this is an example where we're looking at a proportion. This is a one-arm study, and we're talking about the proportion of people that something happened to. The mean is 17%, and the prediction interval is 10% to 27%. Is that clinically important or not? Well, the answer is it depends. Suppose that this was a company that was trying out a new nasal spray that helps with asthma, it helps with hay fever. And they're concerned about how many people might start sneezing after they use the spray. And it turns out that the number of sneezers varies between 10% in some populations, 27% in the others. From a clinical point of view, this might be relatively unimportant because if somebody uses it and they sneeze, they're going to stop using it. For 70% of people, or more than 70%, it's going to work, right? So for them, the distinction between 10% and 27% is not important. They basically want to know if it's around 20% or if it's around 90%, in which case they're not going to use it. That's what matters to them. By contrast, this is actually a plot of patients who are in their 80s or 90s and undergo surgery for mitral valve repair. And the question is, what proportion of them are going to die as a result of the surgery? Okay, because if they have the surgery, they're likely to live another 5 or 10 years. If they don't have the surgery, they're likely to die within a year. But they also want to know what's the chances they're going to be, put out for the surgery and never wake up. It turns out that in some populations it's 10%, and in some populations it's closer to 30%. When this is the clinical outcome, that's a huge difference. I can imagine that if you tell somebody that if you have the surgery, it will help in the long term, but there's a 10% chance you might die, it's very different than telling them there's a 30% chance you might die. So the point I'm making is that even reporting the number, even if we actually used the prediction interval and gave the actual numbers, you can't say that it's large or small except in a particular clinical context. And that's the way I think it should be used. You should report the prediction interval, but then when you're saying that it's large or small, it has to be tied to the particular intervention you're looking at, and you can give your opinion of what that means, and other people, once they have the numbers, can decide whether they agree with you or not. Now, I gave you 3 reasons why the current practice is a bad idea. First, it's based on I-square, which doesn't make any sense. Second, it's the heterogeneity is separated from the mean, which is, silly. And third is that they're using these terms as though they have some kind of an absolute meaning when in fact they don't. I would argue that any one of these reasons alone is a reason not to use those terms, any one of them. And when you have all 3, the fact that the overwhelming majority of papers do this, I think is really something that should be changed. Okay, so the bottom line is this, and I think we're just about on time. I published a number of papers recently sort of making this argument. In this particular paper over here, I'm going to quote a couple of lines from the conclusion. One can imagine a group of clinicians discussing how to address the risks associated with off-hours presentation. That's the one we spoke about earlier, based on the fact that I-square was 75%. Each participant would have their own idea of what the dispersion actually looked like. The group would be trying to reach consensus on what to recommend when each member would be working with their own set of facts. So here we're dealing with the off-hours presentation, and the paper reported that there's significant heterogeneity. So one person thinks that it looks like this, another person thinks that it looks like this, and ironically, they're both wrong because it actually looks like this. And they're trying to decide what to do when everybody has their own idea. Whereas if you actually put this plot up there and everybody was looking at it, they might still disagree about how to proceed, but at least now the argument is going to be based on facts. I mean, they've just spent 6 months or a year or 2 years gathering the facts, and now they have no idea what the facts are. I mean, it's kind of, Okay, the prediction interval provides the information that researchers and clinicians are asking for when they ask about heterogeneity, the information that they believe incorrectly is being provided by other statistics such as I-squared. The prediction interval should be reported as part of any meta-analysis where we have a sufficient number of studies to estimate it reliably. I'm going to close with this. This is a paper that was published in the New England Journal of Medicine in 1997. It was an editorial by this fellow called John C. Baylor III, who was the editor of the New England Journal at the time. And the New England Journal had published this seminal meta-analysis on the use of streptokinase. And it was the first really large meta-analysis that sort of got the attention of the public. And people were starting to do meta-analyses. And he wrote an editorial cautioning people about the use of meta-analysis. He gave 5 different things he was concerned about, but I think he focused on this one. He expressed concern that researchers would not properly address heterogeneity, and that any attempt to reduce the results to a single value with confidence bounds is likely to lead to conclusions that are wrong, perhaps seriously so. We're 25 years later. All meta-analyses use I-squared to quantify heterogeneity. Since this does not provide the information that researchers need to properly address heterogeneity, they resort to focusing on the mean and its confidence interval. And they may reach conclusions that are wrong, perhaps seriously so. And an example of that would be the tocilizumab analysis that we looked at a few minutes ago. By contrast, when we use the prediction interval, we might report, for example, that the intervention is always clinically useful, or that it's clinically useful in some populations but not in others, or that it's beneficial in some populations but harmful in others. And I mean, as Julian has pointed out more than once, with the number of studies that we have in a typical meta-analysis, it might not be possible to get a really clear estimate of what the bounds of the prediction interval are. However, there are many cases when we have a reasonable number of studies that we can report which one of these 3 things it is. That we can report, if you remember those 3 distributions I showed you at the very beginning, that it's clear that it's always helpful. And, you know, it always falls in the range of trivial to large or moderate to very large or whatever it might be. And there are other cases where it's actually going to be where the effect is reasonably consistent across studies, and we get a good estimate of that. And there are going to be cases where it's clearly helpful in some cases and harmful in others. If we can at least get that much out of the analysis, we're doing something very, very important. And again, the tocilizumab analysis is a perfect example of that. And I think this is my last slide, just about. By making this discussion possible, the prediction interval can change the framework about how we think about the results of a meta-analysis. I want to give you a list of a couple of resources. The first one of them is this book that you mentioned before, Common Mistakes in Meta-Analysis and How to Avoid Them. There's a chapter on I-squared and prediction intervals, but I also address many other parts of the meta-analysis where people make equally serious mistakes. The book is free. I'll tell you in a second how to get it, but you can get this for free. There are a number of papers that I published. This one was together with Julian, The Basics of Meta-Analysis. I-squared is not an absolute measure of heterogeneity. This is a commentary in the Journal of Clinical Epidemiology. This is a paper in Integrative Medicine Research, How to Understand and Report Heterogeneity, the difference between I-squared and prediction intervals, the Journal of Physiotherapy, and so on. This is a paper by other people, John Ioannidis, Joanna Intout, making similar arguments to what I've made over here. And the last resource is actually a copy of the slides that we used over here that I promised you before, as well as a recording of this session. The way to get all of them is very simple. If you go to www.meta-analysis.com/papers, you'll find a page where you can enter your email address and click submit, and the server will immediately send you everything except for the slides, because I haven't put them up there yet, but you'll get that in a day or 2. And additionally, if anybody wants to contact me and either get the papers or continue this discussion, this is my email address, biostat100@gmail.com. Okay, and 12:30. Okay, thank you.
Michael, thanks a lot for this inspiring and insightful talk.
Thank
I
you.
enjoyed it a lot.
Thank you.
And yeah, now we are open for any questions by the audience here or also by the audience online. Who wants to start? Gerta Rücker, please.
What do you think is the reason why I-squared made this great career?
Okay. First of all, when Julian proposed I-square, he was doing it for a very important reason. He was working with Cochrane, and back around the year 2000, or a little bit earlier than that, Cochrane was essentially using the fixed effect analysis. So the way that people were using it was to say, this is the common effect. And what they needed was not a way to talk about the actual dispersion of effects. They needed a way to say whether the fixed effect model was appropriate or not. So they essentially needed to distinguish between a case where the effects were consistent and where they weren't consistent. What people were doing at the time was they were doing a significance test for heterogeneity. And Julian recognized correctly that the significance test is nonsense because a significance test based on 5 or 6 studies is never going to give you a significant p-value. So he suggested computing I-square, which is better than a significance test in that respect. Because if you get an I-square of 0, and roughly half of the, I think 45% of the analyses that were published in Cochrane in the year 2000 actually had an I-square value of 0, that tells you that you can use the fixed effect model. I mean, there's a question about whether an I-square of 0 based on only 3 or 4 studies is reliable, but if it is, then the fixed effect model makes sense. And if it's higher, then in many cases, the fixed effect model is not going to make sense. So he was improving the situation as it was. However, as people moved on to do, Cochrane now recognizes that most analyses really should be using the random effects model, where the amount of dispersion is actually important. It was never intended for that. Now, why it hasn't changed, I think it's just a question of people copying what other people did. You see, if I presented a primary analysis and I told you the mean is 50 and the sum of squares is 800, no editor would accept that because nobody has any idea what that means. Similarly, if I tell you the mean effect is a risk ratio of 0.7 and I-square is 70%, nobody knows what it means. But every person thinks that somebody else knows what it means, and they're ashamed to admit that they don't. And also, I mean, in some cases it works. If I-square is very low, in general, there is a small amount of heterogeneity. But it shouldn't be. When I said before that people copy and paste from other papers, if you see roughly 30% of the papers that report I-square say that I-square is the proportion of variance in the observed effects that can be attributed to true effects, and then they proceed to interpret it as though it's an absolute amount of heterogeneity. The first part of the sentence doesn't match the second part of the sentence. Even if they're just reading what they wrote, they should recognize that it doesn't make sense. But the reason that I know there's a lot of copying and pasting going on is because exactly the same phrases show up again and again and again. And I just happened to be reviewing a meta-analysis a couple of months ago where the person that wrote it made a typographical mistake in describing I-square. They spelled one of the words incorrectly. Then I came across another submission where it was the same misspelling. So it was clear not only did they copy the concept, they actually literally went to a journal, did a copy and paste, and plugged it into theirs. And it had nothing to do with their analysis also. But this is unfortunately what's happening. Yes, did you have a question? Gerda, was that it? That's it. Oh, please go ahead.
So the Cochrane 100 still gives these intervals, so this from 0 to 40% and so on.
Mm-hmm.
So why is this the case? Because Julian is the author of the Cochrane. So why didn't they?
Julian, I agree with you completely. I've spoken to Julian about it. His idea, he doesn't call it heterogeneity. He calls it, uses a different word. To me, the two words are essentially the same. And not diversity, forget what it is, but he feels that he's not, he's not, I'm sorry? Inconsistency, that's right. I feel, I mean, I understand the distinction because I spent a lot of time thinking about it, but I think from a real world point of view, people don't understand the distinction. Cochrane now is moving towards prediction intervals. In the new version of the handbook, they include, among other things, the question, you should report it. And I have permission to talk about this. About a week ago, I received a questionnaire from somebody in Australia, I forget where in Australia. She and a group of her colleagues are asking for feedback on a questionnaire if you, and the questionnaire is basically this, if you are reviewing a paper on meta-analysis and it does this, would you consider it to be a major problem, a minor problem, or no problem? And one of the things was if they use I-square to report heterogeneity, and the other one is if they don't report prediction intervals. And I said back to her, I'm really interested in how many reviewers are going to recognize that these are problems. But in constructing the questionnaire, they clearly recognize that this is a common problem. I actually asked ChatGPT how Cochrane feels about prediction intervals. And it said, what does Cochrane think about prediction intervals? And it said, the Cochrane collaboration views prediction intervals as a valuable addition to meta-analyses, particularly for their ability to provide more comprehensive and clinically relevant interpretations of results, and so on. And then they said, despite their advantages, prediction intervals are still underused. To summarize, Cochrane advocates for the routine inclusion of prediction intervals. That had not been my experience. So at the end of the article, it went back and explained where it got that information from. It turns out that most of it is based on that paper by Intout and Ioannidis that I showed you earlier. In addition to publishing this in a journal, they published it in Cochrane. And it since I guess that's the first thing that it found, because it has prediction intervals in the title, it basically, most of the conclusion is based on that, but it's really not typical of Cochrane. I've spoken with the editor of the Cochrane handbook and asked her if she could do it. I submitted for Cochrane that's going to take place in Prague in a month or two. I wanted to do this as a workshop or an oral presentation. And they first they said I should do it as a poster, and then they gave me 5 minutes as part of a series of rapid things. I have 5 minutes to talk and 2 minutes for questions. I'll do it. But the problem is the people that are making these decisions don't understand how important this is. As a matter of fact, there's one more thing, and I'll go into somebody else. I submitted the paper that I showed you that was published in the Journal of Clinical Epidemiology. I submitted initially to BMJ, and the response that I got is they don't want to publish it. And the main reason is that everybody knows this. Everybody knows that you should be using prediction intervals and not using I-square. And I said, I did a survey of your journal. I looked at the last 100 meta-analyses. 3 of them used prediction intervals, 80% used I-squared. She says, yeah, but all the statisticians understand it. I said, yes, but the people that are writing the papers don't. She said, well, there's nothing new here. So I sent it to another journal, and they took it immediately. But that's, I believe if the editor probably is an expert in medicine. If she understood how important this was, she would have had a different attitude. But part of what I said before, people, because it's so commonly used, nobody believes that it's so uninformative, because their feeling is how is that possible? My answer is that people are familiar with the p-values versus effect size estimation. For 70 years in primary studies, people primarily report that the effects are statistically significant or not. And then people think that if the p-value is 0.01, it means there's a very large effect. And if the p-value is 0.2, it means there's a very small effect. When in fact, those things, again, are loosely correlated, just like I-square and the amount of variation are loosely correlated. But at this point, there have been 3 books published about why you should use the effect size, probably well over 1,000 papers. The Journal of the American Statistical Association recently put out an entire volume just of solicited papers exactly on this point, and yet people continue to use the p-value as their primary thing that they're focusing on when they report a primary study. Because the idea is once one of these things becomes entrenched in the literature, it's very, very hard to get rid of it. I actually had a slide over here with this point. This is, sorry. Here it is. This is a picture of three people. That's Ronald Fisher, Julian Higgins, and Simon Thompson. And the point that I made is that each of these people was very brilliant. And the fact that people misuse the p-value is not Ronald Fisher's problem. He came up with a statistic that's very useful when used correctly. The problem is that many people use it incorrectly. Similarly, Julian and Simon came up with a statistic that served a particular purpose when they developed it, and even today is useful if you use it correctly. Sadly, as Julian said, he's English, and the English are very understated. He said, sadly, most of them are using it incorrectly. Okay, I'm sorry. I took a lot of time on that because it's something that I'm passionate about. But who else? Do you have any other follow-up, Gerda? Or, okay, other people have questions, please. Yes.
Well, it's maybe more of a basic question. You told us at the beginning to not confuse confidence interval and prediction.
Yes.
I'm afraid that happened to me, I think. And so, thinking of confidence interval, how would you suggest to interpret it? Because,
yeah. No, it's a good point. I ran through it quickly because I have a limited amount of time. The confidence interval tells you how precisely you've estimated the mean. So in other words, as you add more and more studies to the analysis, the confidence interval is going to become more and more narrow. If you think about the example that I gave of the children in grade school where they're taking a math test, and we're trying to estimate the mean score on that math test. If you have 5 kids in your sample, you might say that the mean is 50 plus or minus 10 points. That's the confidence interval. If you have 50 kids in the analysis, you might say the mean is 50 plus or minus 2 points. If you have 100 kids in your sample, you might say the mean is 50 plus or minus 1 point. The more information you have about the average, the more precisely you can report it. And that's what the confidence interval tells you. By contrast, the prediction interval says, if you take all the kids in the class and look to see how widely they vary, in some cases, it might, let's say you're talking about a class that's tracked. So only the kids that did well last year are put into this class. You might say that the mean is 50 and all the kids score between 40 and 60. On the other hand, if it's just a general class where anybody can get into it, it might be that the mean is 50, but the individual kids score, some of them as low as 10 and some as high as 90. In both cases, the mean is the same, and the confidence interval tells you how precisely you've estimated the mean. And in some cases, the mean is really what you want. I mean, if you have to report this to the state and you want to report what's the average score in your class, they might care only about the mean. But if you're the teacher and you want to know how well the kids in the class are doing, you care very much about the prediction interval, because if all the kids score between 40 and 60, then you're doing something right. But if some kids are scoring 10, you have to worry about them. So different people care about different things. Unfortunately, when you're talking about papers, most of them focus on the mean. For example, in the tocilizumab, the mean is statistically significant. That just means that the confidence interval excludes 0. The estimate is 0.06, and the confidence interval is minus 0.01 to minus 0.12. So if you wanted to show that this worked, that might be what you care about. But like the teacher, what really matters is the prediction interval. For any particular population, what's the effect? Okay. Pleasure. Thank you. Yes.
Thanks. Brilliant presentation.
Thank you.
What I'm kind of struggling with is, so I think the way you describe it for the prediction or the definition that you use is the range of effects across subpopulations, right?
Right. In other words, whenever
indication of that.
I'm sorry. Yes, an indication of that. Yes.
But doesn't that ignore that some of the effects observed in the studies might be due to bias rather than real effects, true effects in various subpopulations?
Yes. In other words, what you're, oh, sorry, was there more to the question?
No, so I just wonder whether that notion of bias, which might be present, should also be at the forefront of mind when interpreting predictions.
Yeah, bias is a very important thing. I mean, one form of bias, for example, is that some of the studies might not have been properly blinded, and therefore the number that you're getting. So basically, when you do a meta-analysis, what you're saying is I have a sample over here of 10 or 20 studies, and I'm trying to make an inference to what the effects will be in a much larger universe from which these studies were sampled. One of the problems is that the effects that you're getting, I mean, this is the whole idea of doing a risk of bias table, is the way that Cochrane recommends that you do it, and I think this is valid, is you do an analysis on the studies that you have and you present that, and then you do a separate chart that says how much risk of bias was there. If the risk of bias is low, then you have confidence that the analysis that you've done represents the actual state of affairs. If the bias is high, then you have a concern that, yes, you have an accurate estimate of what it looks like in these studies, but the studies themselves are not valid, and therefore you really can't count on it. It's a very, very important question, but it's entirely separate from the question. It's not only the question that you're asking should also be asked about the mean effect and about the confidence interval and about the prediction interval. They're all in the same boat, which is that there's this problem that if the studies are biased, what do you do?
I agree, that it's separate questions, but in a way, if we try to educate the community that they should use prediction intervals, that they should interpret in the way that you suggested, that it's an indication of the variation or dispersion of effects. I think we also need to educate them that it might be a misrepresentation because of bias.
I agree with you 1,000%. This is where I chose to, to have my fight, because this is all that I'm doing. But what you're saying, the argument that you're making, I think, is an extremely important argument. Fortunately, it's an argument that's more widely recognized. So you have, all of these groups within Cochrane that are trying to address it. You have, the grade system, which tries to address it. You have the risk of bias table, which tries to address it. It's moving slowly, but I think it's moving a little bit. I mean, if you go to Cochrane, you'll see many reviews that say the results are this, but the quality of the evidence is low because the studies themselves might have been biased. But I still want to reiterate that I think while it's a very, very important problem, it affects the mean and the confidence interval and the prediction interval. So it's kind of separate from what I'm talking about. If the argument that you're making is once we start presenting data in a format that people will understand it, it's more important to get it right. I would agree with you. Okay, thank you. You have a question?
I agree with you that prediction intervals are fine if you have a single meta-analysis. What would you do in subgroup analysis? Would you then calculate prediction intervals for each subgroup?
Yes. Yeah, no, in fact, I didn't have time to show it, but that's what I did in the case of the tocilizumab analysis. I went back and computed a prediction interval. I took the slides out. So I get one curve for the patients that were extremely ill and a separate curve for the patients that are moderately ill. And then you can actually see that one curve falls almost entirely on this side and the other curve straddles both sides exactly. Yeah, there are questions about how to compute the prediction interval in that case. In other words, would you pool the estimates of tau square and then use the pooled estimate? Would you deal with it separate? Those are technical points, but absolutely, you would compute a separate prediction interval for each group. And I think
that the tau values in the subgroups that it's useful to look at them to see whether
it depends on how many studies there are within a subgroup. Because if you're estimating tau square within subgroups, you want to have at least 10 studies within each subgroup to get a reasonably reliable estimate of tau square. So often what Larry Hedges has suggested is you pool the estimates. So if you have, let's say, 8 studies in one subgroup and 8 studies in the second, and it's plausible that the tau square is going to be the same in both subgroups, you pool those estimates. So now you have an estimate based on 16 cases rather than 8, and you apply that estimate to computing both prediction intervals. And I could spend more time on this, but maybe we could talk about it afterwards. In fact, in CMA, you have the option of doing it either way. Okay, other questions, please? Let me see if there are some questions online. Okay, you want to read them to me, ones that you think are... Okay, well, this is actually the question that you asked, unless, yeah. In practice, the Q statistic is often used to decide whether to pool study results or not. How can the PI be used to decide whether to pool or not? It can't. Again, if they're using Q, what they're trying to do is do a significance test to ask if the measure of heterogeneity in one subgroup is different than the one in the other. Those tests are extremely poor. It would be very, very difficult to get a significant value over there. So what I think is I would do it conceptually. If it makes sense just from a knowledge point of view, you talk to your colleagues to think that the variance in this subgroup is going to be similar to the variance in that, it's better pooling. But the way that Larry Hedges explained it to me is that if you're pooling two numbers and the underlying numbers are not exactly the same, then you're going to lose some information by doing that. However, the amount of error that you'll introduce by pooling two numbers that are not exactly the same is several orders of magnitude less than the error you would introduce by estimating tau square based on a small number of cases. So the only time that I would not pool is if I have, let's say, 20 studies in each subgroup at a minimum. And I also believe that the estimates of tau square, that the true values of tau square in the two subgroups are different. Otherwise, I would pool them. And this doesn't apply only to prediction intervals. It's going to apply also to the weights that you assign when you are figuring out the mean effect. It's going to apply to the values that you use when you compute the confidence interval. So it's not a question that's limited to prediction intervals. It's a general question across the whole analysis. Was there another question in the chat box?
You just answered question number 2 from Harry.
Yes. Okay,
I think the first one was implicitly maybe already answered.
will
What
recording,
recommendations do you have for the practice in case of few studies?
okay, in the case of few studies, my suggestion would be not to report it and to explain why. Or, this gets a little bit complicated, when you compute a prediction interval with a small number of studies, the way the computer will do it, whether you're using this program or R or Stata, is it will expand the interval to make sure that it's capturing 95% of all cases. Now, if you have only a few studies, it's going to expand the interval way out. And in a sense, that's accurate, because if you want to capture if your goal is to make sure that you captured 95% of all populations, it really will be a very big interval. The problem with that is that it's going to be so wide that it looks ridiculous. I mean, if you have a risk ratio that goes from 0.2 to 0.8, it's not useful. What you can do in a case like that is not make the adjustment. In other words, simply use the mean plus or minus 2 standard deviations, in which case the interval is going to be much more narrow. Now, I would be very clear in explaining that we don't have any confidence at all that 95% of the cases are going to fall within this range. But our best guess of how widely it varies would be this. Don't use it to give yourself an estimate of what the range of effects is. But if you want some general sense of how widely the effects vary, this is the best estimate we have based on the 3 or 4 studies. It's very unreliable. It's not different than what happens if you're reporting TOR squared. Those numbers based on 3 or 4 cases or 5 cases are going to be extremely unreliable. So if you think about it, the way that you are computing the prediction interval is the mean plus or minus 2 TOR. It's just as unreliable as TOR, plus it's also unreliable based on the mean shifting. My preference would be probably not to do it at all, but if you do it, include that disclaimer. I mean, imagine if you submitted a primary study to a journal and you told it you had five patients in the study. I mean, what journal, nobody would even think of doing that. When you're submitting a meta-analysis with 5 studies and it's a random effects analysis, your effective sample size is not the number of people, it's the number of studies. You're trying to do an analysis based on a sample size of 5. And when you do that, you don't have enough information. Because remember, what you're doing is you're figuring out, you have 5 studies. You're assuming that the mean in each one of them is different. And now you're taking an average of those means, and you're trying to figure out how much variation there is among those means. That would be analogous to a primary study if each of the studies had 1 million people in it. If each of the studies had 1 million people in it, you have 5 estimates. You really know the true effect over here, and you know the true effect over here, and here, and here, and here. So you're working with an N of 5. The fact that these studies that would be if each study had 1 million people in it. The fact is each study might have 30 people in it. So in addition to the uncertainty that you get by working with an N of 5, now you have the additional uncertainty that you don't actually know the true effect for each of those 5. So in other words, the best case is that in each study you have an infinite number of people. The real case is that in each study you have a limited number of people. But the fact that you have a limited number if you have 1 million people, it doesn't add to your precision. It simply means you're not losing precision. But the most you can hope for in a sample size is the number of studies when you're dealing with the random effects analysis. If you're dealing with the fixed effect analysis, it's different. I'm probably going through these things so quickly that the people that understand it get it, and the people that don't are not gaining anything. But these are the kinds of things like, you could talk about for an hour, but they're all important things. Okay, other questions, please.
Other questions?
There probably are some more online. Somebody, go ahead.
I have also a question.
Please.
You mentioned that we have to be careful and critical about the Q test and also about I-squared. But unfortunately, they are always in all standard outputs of softwares I know. Whereas the prediction intervals is often not a standard output. For example, also on Ref and Web, it's not yet part of the output. And so my question is, would you say that it does more harm to do it as default when you generate a forest plot output and you include them by default? Does it make more harm, or does it more useful?
I would say it's harmful. I'd say it would be better not to include it. Many years ago, I have the great pleasure of working with Larry Hedges and Julian Higgins now for I met Larry in 1996. I met Julian a few years after that. And these are two of the smartest people that I know and very generous with their time and everything. As a matter of fact, when we were writing the book, the first book, Introduction to Meta-Analysis, I said, this goes back to your question, Jörg, about somebody's question, I'm sorry, about why it's so common. At some point I said, why are we even reporting to a square? Let's just report I squared. It goes from 0 to 100. Everybody gets it. And Julian sort of hit me upside the head and he said, you don't get it. It doesn't tell you what you need to know. So even I, at one point, got so involved in this that I missed it. But what Larry, I'm sort of interrupted myself. What Larry said to me is that the way people think about research, the way people think about statistics, depends largely on what language we have for talking about it. And he said, when computer programs generate numbers like I square or Q or P values and so on, people see those numbers and those are the numbers that they use when they're writing their papers. He said the way to change the way people think about research is to change the language that they have. And the way to start that is to change the computer output. And absolutely, I think, as I said, I've spoken with people at Cochrane to very little effect. I think I spoke with you on the phone last week about this very question. Cochrane moves slowly. It's a large organization. My belief is that at some point they're going to put this in, but it's going to take a while. Yeah. Okay.
Question.
Okay.
This is
Let me just one chat. They wanted to know if there's going to be a recording for this. Some people who came in late might not know it, but there absolutely is. So here, let's see. Let me just go back to that slide again. Here it is. If you just go to metaanalysis.com/papers and type in your email address, or if you send me a note personally to biostat100@gmail.com, I will send you a copy of the slides. I can link you to a recording of this. Additionally, you'll get a copy of the book and a copy of all of these papers. So please do that. Okay.
There is another question in the chat. I don't know how familiar you are with the grade concept.
Yes.
This question is about the grade. How does the prediction interval impact the interpretation of imprecision in grade?
Okay. Yeah. Okay. I actually looked this up yesterday because I thought somebody would question me about that. The answer, what grade says, I should have a copy of it in here. Okay, here's grade. It says inconsistency, a simple rule of thumb. When studies yield widely differing estimates of the effect, you should look for reasons for heterogeneity. I think bottom line is this. As I mentioned at the very beginning of this talk, there was a time that the goal of a meta-analysis was to find the common effect size. So the hope was that all of the effects would be very similar to each other. And therefore, if you report the mean effect, you're also reporting the common effect. And what's nice about that is now you know how well this is going to work. And what people said in those days is that if it turns out that the effect size varies, that downgrades the information that you have, because now if you say to somebody it's going to work, in half the cases you're going to be wrong. For half the people it will work, for half the people it won't work. So the quality of the information is downgraded. And that still corresponds over here to what grade is saying, which is that if that's your goal, if your goal is to report a common effect, then any inconsistency is going to downgrade the value of the information. However, they also say that if you have heterogeneity, which they're also calling inconsistency, then the first thing to do is to look for reasons for the heterogeneity. So for example, in the tocilizumab analysis, there is a lot of heterogeneity, but if you then go ahead and look at it, it turns out that in one population, it's clearly associated with benefit, and in another population, it's clearly associated with harm or not benefit. So they recognize now that it is not the case that you only need to be looking for a common effect. If you're looking for a common effect, and the way that they discuss that is that you can't think of any reason to explain the heterogeneity, then indeed heterogeneity would downgrade the results. But if you expect to see heterogeneity, and once you get it, you can then look for the variables that are associated with that. That's fantastic. I mean, think about how useful. Look at the tocilizumab analysis. If you look at that and you recognize that in some places it's harmful and in some it's helpful, then you can do additional analyses and find out that there's reason to believe that in these patients, it's going to save lives, and in these patients, it's going to harm them. I mean, think of how much more useful that is than simply saying, if you have something that actually works well in one population and not another, how important it is to find that. In some cases, it's going to depend on the populations that are being used. In some cases, it might depend on how the intervention is being administered. For example, one of the analyses that I mentioned briefly before about ADHD, it turns out that some studies administered the dose in one way, and some administered the dose in a different way, and that made a huge difference. So in that case, it wouldn't even be a question of saying it works for these people and not for those. It works for this method of giving it, but not for that. I think, see, primary studies can only give you the effect in one population. And a meta-analysis based on very similar populations can only give you the effect in that population. But the beauty of a meta-analysis is that you're not limited to one population. You can include multiple populations, and then either it turns out that the effect is more or less the same across them, and if it isn't, to look for variables that are associated with that, whether it's the kind of people that are being enrolled, or the type of intervention that's being used, or maybe the way you measure an outcome. And as I said, I think GRADE is now beginning to, it's not perfect, but they're taking a step in that direction. Okay.
Further questions? We are already more or less at the end of our session today. I still have one final question, a very general question.
Yes.
What would you recommend us as researchers, as health scientists, methodologists, statisticians, what would you recommend us to get into contact with other researchers and exchange a little bit about this topic? How would you do it to spread this idea a little bit more? Do you have some recommendations?
I haven't thought about it a lot, but if you can send those people a link to this recording, that would probably be a good start. I mean, I'm serious. I gave a talk like this a couple of years ago to people in Vancouver, and to some extent, they sent out links, and some people are aware of it now. I mean, what I really would like to do is to present this to a large group at Cochrane and have more than 5 minutes to do it. Because I think once people hear it, it's going to catch on, but it's not that easy. I mean, I really have been trying now for a long time. I said before that when I first asked Julian about this, and this goes back to Cochrane in Colorado, which is 15 years ago, he said that he had been talking to people about this for years and didn't get any place. And therefore, if I wanted to write a paper, he would join me. And I thought, sure, but now it's 15 years later, I'm not having any more success than he had. And so if people have ideas, please let me know. I'm very open to that. Yeah. Okay, thank you very much. Thank you again, Jorg, Voldemar. I really appreciate the opportunity. It's very nice to meet everybody. Okay, and I did give you my email, so if you want to continue the discussion, please feel free. Okay.
Perfect. Michael, thanks a lot for your presentation. We have some little presents here for you.
Oh.
There, as your topic about heterogeneity, I have also some very heterogeneous presents for you. So sometimes if you, for example, in the evening, you might have a little wine from Freiburg. Then you wake up in the morning and you probably are a little bit tired. Then you would need a coffee, which is also like not this rösten. If somebody know what rösten is.
What?
It's roasted. It's roasted in Freiburg.
Oh.
We have not coffee directly in Freiburg, but it's roasted in Freiburg. And if this might be a little bit irritating for your stomach, all of this, then we have also good herbal tea for you.
Is that made in Freiburg?
I have to say it.
Okay. Well, thank you very much. I wasn't expecting that. That's wonderful.
So, this is everything for you.
That actually is exactly what happens to me.
Germany,
thank you so much. That's what happens to me every night and every morning. How did you know? Okay. Okay, thank you, everybody. It was really nice.
If you would like to stay here for together, we should have some coffee and drinks.
And don't worry about it, because I have over here, after the drinks, I have